First of all, I'd like to say it's a pleasure for me to have a chance to participate in this meeting, and I want to thank the organizers for inviting me. Some developments in mathematical research have come about through attempts to solve special problems. Others have started with the pursuit of ideas. This lecture is an historical sketch covering roughly the 8-year period from 1926 to 1934 of the pursuit by Emmy Noether and others of the idea of applying non-commutative methods, especially the theory of central simple algebras, to commutative algebra, and in particular to algebraic number theory. The principles, besides Noether herself, were...
No. I'd be very interested in doing something like that. I mean, maybe there's some mysterious connection between tight closure and test ideal theory and the theory of multiplier ideals that Rob's going to talk about. And there are overlapping applications. But the exact connection is mysterious. Yeah, in fact, I didn't put on my list of 11 things, but this is the one that doesn't work.
It's not that mysterious. I mean,
Yeah, no, I know there.
There's no definition in terms of intervals. That's the deal that are required.
Well, Q. Gorenstein. I mean, you need some
Well, yeah. But appropriate-
conditions
appropriate
under.
context.
Yeah. Yeah, so this is another example of this feeling that even in regular rings where tight closure doesn't do anything, that it's useful. And the theorem, the proof is short, and the characteristic P proof is short, and I'm going to include it in the notes, but I'm not going to actually do it because I can see that I'm way behind schedule in terms of what I'm going to cover, so I have to agonize before my next talk about what to leave out, but I will mention this. So this is the Ein-Lazarsfeld-Smith comparison theorem. And now their theorem is in characteristic 0, and it's proved using asymptotic multiplier ideas, and hidden in there are things like resolution of singularities and some deep vanishing theorems. So I claim it's hard, and it's in Inventiones to prove it. But in fact, if R contains a field, so they didn't do the characteristic P case, but of course Craig and I couldn't resist the challenge. I'm just going to state this in the very simplest possible case. So let's say P is a height P prime of R. And then
which of these P's?
That was maybe
There's-
the height of the...
capital P is okay. Let's not confuse any. Oh, what did I say? I height H. Sorry. Hold on. Let's. I didn't mean to make the height of the prime. But the audience needs to be amused at this stage in the process. Whoops! I lost the mic. What was this on a button?
No, there's enough times.
Oh, it was just. Okay, thank you. So, so this is the symbolic power, where p to the symbolic power t is p to the t, and the ring R localized at p, but contracted back to R. So it's the stuff that's multiplied into the tth power of the prime by something that's not in the prime. And the symbolic powers, it's kind of hard to understand just how big they can be. So I think everybody was amazed at this theorem. It was unexpected. And as say, the characteristic zero proof is difficult. And there is a tight closure proof of it, and it's just a few sentences, but I'm not going to try to give it here. And in a way, this theorem is closely related to the Briançon-Skoda theorem. The proof will remind you of it if you look at it. And of course, what you do is you don't directly prove that this is.
R is regular.
Did I not say that?
No.
Thank you. I mean, I think I did sort of I said it was an example of another one of these instances where tight closure is useful in regular rings. So, of course, what you do is to prove that this is in the tight closure of p to the n. And that's also true without regularity if R mod p has finite projective dimension. You still need tight closure here. I think that's very hard by analytic methods, but it's the same proof using tight closure. So it's another instance where I hope to convince you that tight closure is useful. I mean, it doesn't come up in the statement of the theorem. It's okay.
May I ask a question?
Yeah.
In what way is this that R mod p has finite projective dimension? How do you take advantage from that to apply here?
The key point is that P bracket Q is unmixed. That's okay for experts only. That's what you're, so that when you that's where you use finite projective dimension. And that's, so it's connected with the flatness of Frobenius, in a way, in the regular case. Okay, well, the thing that I want to talk about next, both as an application of tight closure to a theorem where you don't mention tight closure, which I consider the kind of thing that proves it's useful, but also it raises the subject of colon capturing, which I talked about in my list of 11, except I think I called it controlling your colon. But so this is a theorem that it was actually first proved by a different kind of characteristic P technique. It's really, the proof really wasn't actually a hidden tight closure argument. It's a little bit different. But so originally, I did this with Joel Roberts. And it says that if R is a Noetherian K algebra, regular, and G is a linearly reductive algebraic group, over K, with a suitable action on R. So a knack. Well, maybe I can.
It's much easier for somebody else.
Okay. I'm going to make you earn your salary. We'll see how many more times I can. I only have 15 minutes left, so probably not too many more.
Actually, the wire in your case should go on the other side.
Is that what's...
You want me to do it? It doesn't matter.
let's try it this way.
The next time.
Next, okay. But that's tomorrow, right? We'll see who comes back after this. Okay. So D is a linearly reductive algebraic group over K, and acting on R in the appropriate category. Linearly reductive means that every representation is completely reducible, and there aren't so many groups like that in characteristic P. But in characteristic 0, that's the same as reductive, where it's those groups over the complex numbers are complexifications of compact real Lie groups. And so the conclusion of the theorem is that RG is Cohn-Macaulay. The ring of invariance, that's the fixed ring of the action of G, is Cohn-Macaulay. Now, in this situation, for a linearly reductive group, there's something called the Reynolds operator, and so it's a G module retraction, but it also happens to be RG linear, and that's all I'm going to use. So there's an RG linear map. It's not an algebra map. It's from R to RG, i.e., if you like, the inclusion of the ring of invariance in R splits as a map of RG modules. And so, in fact, the theorem that Craig and I eventually proved, which this proof really didn't do the generality that I'm about to describe. What's actually true is that if S is regular and R to S splits as a map of R modules, this implies R is Cohn-Macaulay. And I'm going to mention without doing it that this reduces to the case. One can reduce to the case where R is local and complete. Now, there's also a proof in geometric cases, and it's even of a better result, because it says that when you have this condition and S has rational singularities, then R does. That's due to Buteau. The proof that Buteau's argument, in the end, depends on resolution of singularities and the Grauert-Riemann-Schneider vanishing theorem, which is like a souped-up Kodaira vanishing theorem. And at least in its original proof, that depended on analysis. There is an algebraic proof of it these days. But Buteau's proof was sort of another instance where one seemed to be able to use methods originating in analysis to get algebraic results, and it was kind of intriguing. But I'm just going to talk about this theorem and how one uses tight closure to do it. And by the way, since most of the reductive groups are, characteristic 0, This is a primarily characteristic zero theorem being proved by characteristic P techniques when you analyze it. Let's see. So till 12:20 on that clock is okay. So before giving the proof, I want to talk about this business of tight closure and colon capturing. And I'm just going to do it in a simple case where I can give all the details in a simple case, and it's an easy argument. But quite generally, if R is I'll just say it for domains. If R is a local domain and nice, so excellent is enough, and x1 through xk plus 1 is part of a system of parameters. What multiplies xk plus 1 into this ideal is contained in the tight closure. So the tight, in a nice ring, and nice there might mean Cohn-Macaulay, then xk plus 1 would be a non-zero divisor mod the previous parameters. That's the definition, that systems of parameters form a regular sequence. And you wouldn't need tight closure. Okay? So here, tight closure is making up for the failure of the Cohn-Macaulay property by capturing what's these zero divisors. So I actually want to prove that statement because it's a very short, easy proof. So the idea is but I'm only going to do it in the complete local case. So let R be complete local. And for simplicity, I'll assume it's a domain. But this case is enough for doing this theorem about the rings of invariance. And in that case, take a coefficient field and put the system of parameters into a power series ring in there. I'll call this one A. A is regular. R is module finite over A. And now suppose we have u times xk plus 1 is in the ideal generated by x1 through xk in R. The claim is that u is in the tight closure of the ideal generated by x1 through xk. So here's the trick. R is this torsion-free A module. It's a domain, and it's finally generated over A. So there's a biggest free A module in there. Choose AH contained in R free. And if the rank of this thing is as big as possible, the same as the torsion-free rank of R over A, the quotient will be torsion as an A module. And pick C in A non-zero such that C times R is contained in this free A module. right? So now the x's do form a regular sequence on A in the regular ring, it's clear, and so they do form a regular sequence on this free A module, okay? And now, look at this equation, and let's raise it to the qth power. So u to the q, xk plus 1 to the q, is in the ideal generated by the qth powers of the x's times r. Well, now I want to multiply by c. So cu to the q times xk plus 1 to the q is in the ideal generated by the qth powers of the x's. But c times r is actually inside this free A module. I can actually write AH. Okay? But these qth powers of the x's are a regular sequence on AH. So working here, this is I'm getting that cu to the q belongs to x1 to the q through xk to the q AH. Okay? Here I've just got this free module over the regular ring. So xk plus 1 to the q is not a zero divisor on this ideal times the module. That's true in each component separately. But AH is inside R. Right? It's this biggest free A module that's inside R. I hesitate to say this, but we're done. That's all Q. As I say, these arguments are embarrassingly simple. Okay. Well, I know it's very hard to follow people doing this stuff at a blackboard in a lecture like this after you've been through 3 hours. I mean, we're getting close to 3 hours now. But still, if you sit down with it, if you're interested and you sit down with it, I think you'll see that this actually is very easy, which is good because I'm almost out of time. Now, suppose that R, let's see, when I stated this theorem, what were the two rings? I sort of lost track. R and S, okay. So now here, R is a direct summand of S regular. I claim implies R is Cohn-Macaulay. And I'm going to assume here that R is complete local, for which you can get to that case easily. And here's the point. First off, if U is in the tight closure of I, this is in R. That implies U is in the tight closure of S, I and S. But S is regular. So U is in R intersect IS. I'll write that as R plus 0. Remember, S we can think of as R direct sum some other R module. So in fact, this intersection is just I. what I've just shown is that if you have a ring in which every ideal is tightly closed, and you take a direct summand of it, you have that property again. So in R, I equals I star for all I. And now, let's look at this colon, thinking in R, but knowing that every ideal is tightly closed. Well, remember, what we just proved is that quite generally, when you take that colon, you wind up in the tight closure. Just any old R. But because R is direct summand of regular, the tight closure is the ideal. We're done. This shows that the system of parameter consisting of the x's is a regular sequence. xk plus 1 is not a zero divisor on this. If it seemed like magic, it's because it was. You may think I cheated, but I didn't. And this proof is valid in characteristic P and characteristic 0, both, once you get tight closure theory going in both places. So you can give the same proof. Okay. That's it for now.
Questions or comments?
Is this last theorem known in mixed characteristic?
No, it's an open question in mixed characteristic. Yes.
So this is so R is sort of a special Cohen-Macaulay ring. It's things whose ideals are tightly closed. Is that true for all Cohen-Macaulay rings? Or?
No, because remember, k of xyz mod x cubed plus y cubed plus z cubed is Cohen-Macaulay isolated singularity.
So this is something sort of image. So this property somewhere in the
Yeah. So I was going to say this eventually. Rings with this property are called weakly F-regular. And if their localizations have the property as well, they're called F-regular. It's not known whether those two are equivalent, at least unless somebody's done it since and didn't tell me. It's still open. But it's believed that weakly F-regular actually should localize, and therefore it should be the same as F-regular, and then we could drop the weakly, because it's kind of annoying. It's known in some cases, like Gorenstein rings. Sorry? Graded.
finally generate over a big.
Yeah, yes. It's known in a lot of cases, but it's not known in general.
Is R a direct summand as an R module?
Yes, that's the idea. R is direct summand of S as an R module. That's a pretty subtle condition when it's not module finite. Maybe I'll do, I think in the next lecture I'll actually exhibit a ring of invariants or a couple of them, so you can see that it's something pretty subtle happens there.
After this morning, I realized that I've prepared much too much material for these talks, so I'm going to have to be rather ruthless in cutting out various things that I was going to say. So if you notice some leaps in the page numbering, that's what's happened. I also added in some pages. Really shouldn't have done that, but I wanted to connect up with some things that you might already know about. So the first thing I wanted to point out was that a lot of you may know Mashka's theorem, which says that if you're working with representations of a finite group in coprime characteristic, then every short exact sequence of modules splits. In other words, whenever you've got an invariant subspace, there's an invariant complement. And the way to interpret that in terms of cohomology is that it says that X in positive degrees of anything with anything else vanishes. So in particular, group cohomology vanishes in degrees bigger than 0. I also wanted to say a few words about how on earth you compute group cohomology in response to a question this morning. So the fact that the order of the group annihilates group cohomology, or group cohomology is 0 in coprime characteristic, says that you really only need compute at characteristics dividing the order of the group. And then there's something called the transfer map, which tells you that if you have a Celoff P subgroup, then the restriction map is injective. And so the way that you calculate group cohomology is, first of all, you calculate the cohomology of the Celoff P subgroup, and I'll get to that in a minute. And then secondly, you use this Cartan-Eilenberg stable element method, which says that you can actually identify the image of the restriction map as the elements in the cohomology of the Celoff P subgroup, with the property that whenever you've got two subgroups of the Celoff P subgroup that are conjugate in the big group, then you can either restrict down to the first subgroup and then do the conjugation, or you can restrict down to the second subgroup. And you'd better get the same answer if the thing was in the image of restriction from the whole finite group. And in fact, it's an if and only if. If an element is stable under all these conjugations, then in fact it's in the image of restriction. So that's a characterization of the image of restriction. This is called the Cartan-Eilenberg stable element method. So if you're a P group, then you can either compute by hand or by machine. Yes, this was the one that we need to adjust. Is that about right? If you're a P group, you can either compute by hand or by machine, and the methods are actually quite different. By hand, you start off by doing cyclic groups explicitly by computing an explicit resolution, and then for a general P group, you use induction on the order. You choose a central cyclic subgroup. There always is such a thing. And you use either the Linden-Hochschild-Sayre spectral sequence, which is a spectral sequence going from the cohomology of the quotient and the center, going to the cohomology of the group, or you use the Eilenberg-Moore spectral sequence, which actually sometimes computationally turns out to be easier, even though it's more complicated to set up. And the Eilenberg-Moore spectral sequence was actually used by Dave Rusin to compute the mod 2 cohomology of the groups of order 32. Smaller two groups had actually been previously computed. And the Linden-Hochschild-Sayre spectral sequence was what was used by Dan Quillen to compute the cohomology of extra special two groups. Or you can use machine computation, and here John Carlson is the world expert. And the way to do it by machine is you just build an explicit resolution of K as a KG module. And actually you don't build the modules in the resolution, you only build the maps, because the modules are much bigger than the maps. So the maps are just matrices of elements of the group algebra. If you actually store that number of copies of the group algebra, you're going to use a lot of space. And so you're just playing with matrices of elements of the group algebra. And the one question is, when you stop resolving, and the third lecture that I'm going to give tomorrow will explain some of the commutative algebra behind how you tell when to stop. And John Carlson actually computed the mod 2 cohomology of all the groups of order 64 this way. There are 267 of them, by the way. And some of these groups have quite complicated cohomology. I also wanted to connect up with the last talk of this morning. Namely, if you've got a normal abelian Celoff P subgroup in characteristic P, then what this Linden-Hochschild-Sayre spectral sequence tells you is that actually the cohomology of the group is just the invariance of G modulo the Celoff subgroup, which is a P prime group, on the cohomology of that Celoff subgroup, which is an abelian group. So you know its cohomology very explicitly. So this is an invariant theory calculation. And here the inclusion of the cohomology of the whole group into the cohomology of the Celoff subgroup splits. That's because of the transfer map. And so the cohomology of the whole group is actually Cohen-Macaulay. In this case, for actually easier reasons than was explained by Hoxter this morning. So now I want to get back to what I was saying at the end of this morning and carry on talking about associated primes. So this is the last slide I put up this morning, and it explains how group cohomology with FP coefficients admits an action of this steamrod algebra. Inside the group cohomology, you can always find a copy of these Dixon invariants. So this is the invariance of the general linear group on the polynomial ring. This polynomial ring really comes from an elementary abelian subgroup of maximal rank. You have to dilate the generators by raising them to some p power to be able to find them in there, but there's always a copy of these in there. And you can use these Dixon invariants as a homogeneous system of parameters. And I'll explain the advantage of doing that, which really... Oh, but before I do explain the advantage of doing that...
Sorry, I'm a little unclear where the Dixon invariant sit with respect to the steamrod algebra.
So the steamrod algebra acts on any polynomial ring because it's just the cohomology of some space, and so it's going to act on these invariants. And actually the steamrod operations kind of connect these one to the next. There's a very standard action of the steamrod algebra on these Dixon invariants, which is described. There's a paper by Clarence Wilkerson from about 20 years ago which gives a very explicit set of formulae for the action of the steamrod algebra on these Dixon invariants.
So these are going to be, we're going to get a homogeneous system of parameters
in the cohomology of any group.
And why is this ring mapping into the cohomology of any group? I've lost some of the pieces. You took a representation.
What you do is you take a elementary abelian subgroup of maximal rank, or rather you actually have to match up Dixon invariants from the various different elementary abelian subgroups of maximal rank, and lift them back to elements in the cohomology of the whole group. But in order to lift them back, you're going to have to raise them to some p power.
And the reason the invariants come in is because the group acts through this GLR of FP.
Yeah, the normalizer is some subgroup of GLR FP, or the normalizer modulo the centralizer will act as some subgroup of GLR FP. So those invariants are always in the invariance of the normalizer modulo the centralizer. So where are we? Yes, so there's something called the Landweber-Stong conjecture, which is no longer a conjecture because it was actually proved by Bourguiba and Zerati, which says that if you have one of those occurrences of the word module should say algebra. If you have an unstable algebra over the steamrod algebra, which is simultaneously a module over the Dixon invariants, with the compatibility condition that comes from this inclusion, then actually the depth of such a thing is always the longest initial segment of that set of Dixon invariants, which forms a regular sequence. So actually, you just need a single test sequence to test for depth. You just look at how many of these Dixon invariants form a regular sequence, and that gives you the depth. So that it means that large enough steamrod operations give 0 on an element. It's a condition that's always satisfied by the cohomology of a space, but not by an arbitrary module over the steamrod algebra. So the upshot of this is that there's a single test sequence that you can use to establish what the depth of the cohomology ring of a group is. So there's actually a conjecture by John Carlson that is strongly associated with this, which is if you have a finite group in a field, then the cohomology always has an associated prime whose dimension is equal to the depth. This is not at all true of arbitrary graded commutative algebras over a field. So this says something very special about the cohomology of groups, and it's true in every computation that we've ever done. There's also some sort of conceptual reasons why it might be true, but there's no proof around yet. But actually, the possibilities for associated primes are very limited for the cohomology of a finite group, because one of the things about the action of the Steenrod algebra is that the annihilator of any element, the radical of such a thing, is always Steenrod invariant. So a Steenrod operation always takes something in the radical of annihilator to something else in the radical of the same annihilator. So associated primes in particular are always Steenrod invariant. And it turns out that in a cohomology ring there are not very many Steenrod invariant prime ideals. I mean, there are an infinite number of prime ideals in the ring in general, but only a finite number of them are Steenrod invariant. And actually we know exactly which prime ideals are Steenrod invariant because of a theorem of Serre, which says that the Steenrod invariant primes are actually just the radicals of the kernels of restrictions to elementary abelian subgroups. So Serre actually proved this in the case of an elementary abelian group itself. But then, if you combine that with Quillen's theorem, you get it for an arbitrary, say, compact Lie group. You get that the Steenrod invariant primes for any compact Lie group are just the radicals of the kernels of restrictions down to elementary abelian subgroups. So somehow there's a 1-1 correspondence between Steenrod invariant primes and conjugacy classes of elementary abelian subgroups of the group. And those primes are the ones from which the associated primes must be taken. So the associated primes are among these Steenrod invariant primes. So there's just this finite list of possibilities for which are the associated primes. And the problem is trying to determine which elementary abelian subgroups correspond to associated primes. Only some of them correspond to associated primes. And it's very hard to tell which. If someone could come up with a way of looking at a group and telling which elementary abelian subgroups correspond to associated primes, we would be very, very grateful.
What's the first class of groups for which this is a problem? P groups with...
Well, first class of groups for which is a problem.
I mean, how you say you would be very grateful, but how
well, it's tough even for small p groups. So for example, here's an interesting example. If you take groups of order p cubed, for p odd, there's just one isomorphism class of non-abelian groups of order p cubed and exponent p. These are called extra special groups. And for p equals 3, that's Cohen-Macaulay. And for p bigger than 3, there are one-dimensional associated primes, so it's not Cohen-Macaulay. So, you have to find some way of distinguishing between p equals 3 and p bigger than 3 in that case. Well, most of what I've said so far I've just really talked about the commutative algebra. To get a bit further with understanding the commutative algebra of the cohomology ring, you really have to do some module theory. And unfortunately, the module theory you have to do is quite deep. And I want to try and explain a bit of the module theory that comes into the picture before coming back to the commutative algebra, and then I'll explain how it gives some input to the commutative algebra. There are a lot more details of what I'm saying in the notes that you can find in the library, by the way. Where have I got to? The middle one. So the next thing to explain is about idempotent modules and varieties. So let's see, how should I explain this? So if G is a finite group and the characteristic of K is P, let's have a look inside the maximal ideal spectrum of the cohomology ring. So this is the object that really Quillen completely described and I told you about this morning. And so Quillen's inseparable isogeny just says that all you're doing is you're taking these elementary abelian groups, which give you little affine spaces, and you're twisting them up and gluing them together to make the variety of the whole group. So inside that variety, what we're going to do is associate to any finitely generated KG module, we're going to associate a subvariety of that. And these subvarieties are going to control cohomological properties of the modules. And so it turns out that this is going to be a lot easier for finitely generated modules than for infinitely generated modules, where I have to do something a bit more complicated. But we're going to have to talk a little bit about infinitely generated modules, because actually that's part of the game that you have to play in order to get out information about the commutative algebra. So it's a bit of an involved game, but let's try and stick with it. So the original game for finitely generated modules goes as follows. If you have a finitely generated module, then there's a natural map from the cohomology ring to the Xth ring of that module with itself, just given by taking an n-fold extension of the trivial module by itself and tensoring over the field with your module to give it an n-fold extension of your module with itself. Okay? Remember, we're tensoring over a field with diagonal G action here. Tensoring over a field is exact, so this takes exact sequences to exact sequences. And so it gives you a map from X to X. And this map has a kernel. And that kernel is just some ideal in this ring. It's a graded ideal. So it defines for you a closed homogeneous subvariety of the cohomology variety. And that subvariety we're going to denote by V sub G of M. And by the way, if you don't like X of M comma M, you get exactly the same answer by taking the intersection of the annihilators of the simple modules with M or the intersection of the annihilators of X of any module with M. So actually, you have a little bit of flexibility as to what you use for the left-hand slot of X. So, 23. So here are some properties of these varieties. The first is probably the most important property. You can tell whether a module is projective just by looking at its variety. And this is actually very often used as a way of checking that a module is projective. So it turns out that these varieties are very easy to compute, actually, because there's a way of determining the varieties just by restricting down to elementary abelian subgroups and computing some determinants. So actually, the computation of these varieties doesn't involve knowing any cohomology. these varieties also behave very well with respect to direct sum and tensor product of modules. Direct sum of the modules gives you the union of the varieties, and tensoring modules gives you the intersection of the varieties. So actually, this gives you a very good way of telling whether a tensor product of two modules is projective.
Can I ask a question? So
Yes.
you're saying you can compute these varieties VGM without having previously computed VG?
Yes. Well, VG is just a question of, you think of VG I mean, if you think of it at the level of points as this limit of varieties of the elementary abelian groups, then you don't need to know anything about G except its subgroup structures. You don't need to compute the cohomology of G. You only need to know the elementary abelian groups and how they glue together. So inside that variety that you build from the elementary abelian groups, you just compute at the elementary abelian groups by playing with matrices. And it's a very easy computation. I won't give you an example because it would take too much time, but...
Could you say something nevertheless about this limit? You're taking a bunch of affine spaces.
Yes.
And identifying them.
Identifying points. So anytime a point in one of these affine spaces gets conjugated to a point in one of those affine spaces, you identify those points.
Is this a rational variety, for example? Is there an open subset which is one of these? Is there anything nice like that?
Well, you can stratify it by layers which consist of taking an elementary abelian subgroup, so that's an affine space, removing all the rational subspaces, FP rational subspaces, and just quotienting by the normalizer. So if you take all those pieces and glue them together according to how the subgroups include, that will give you the variety.
How do you get the non-reduced structure?
That's much more complicated.
But is there a way of thinking about it?
No. Unfortunately not. That would be absolutely great if that were true, but it's not. One of the things that is remarkable about these varieties is that every subvariety of the cohomology variety is of the form Vg of m for a suitable m. And the way you see that is, first of all, you get the hyperplanes by a particular construction, namely, if you take an element of cohomology, you can build a module out of it. Namely, you can think of this element of cohomology as being represented by a cocycle, which is a map from the nth kernel in a resolution of k to k. So there's your representative cocycle. If zeta's non-zero, that map's going to be surjective because k doesn't have very many submodules. You take its kernel. The kernel of that map we write as L zeta, and the variety of L zeta is just the hypersurface determined by thinking of zeta as an element of the coordinate ring of Vg. Okay? So now if you take an arbitrary subvariety, closed homogeneous of course, you can write it as an intersection of hypersurfaces and just tensor together those L zetas. And that will realize an arbitrary subvariety of the cohomology variety. So I've got that written down as at the bottom here. So you choose zeta 1 up to zeta t in such a way that your variety is the intersection of the varieties determined by these hypersurfaces. And then you just tensor together the corresponding L zetas. Infinite dimensional modules are, of course, slightly harder than finite dimensional modules. And you may wonder why on earth we're interested in infinite dimensional modules, which is a very good question. So I'm going to say two things about why you might be interested in infinite dimensional modules. The first is there are various constructions in representation theory that naturally give infinite dimensional modules and that we are interested in the answer to. In particular, if you have representable functors on the module category, very often it turns out that the representing object is not actually a finite dimensional module, it's an infinite dimensional module. There are a lot of modules that we build this way. If you want to think of an analogy, in algebraic topology, even if you're only interested in finite CW complexes, you start doing homology theories on those, or cohomology theories on those finite CW complexes, and you find you want representing objects for them. Well, the representing object for ordinary cohomology, for example, is an Eilenberg-MacLane space, which is not a finite CW complex. So you're automatically dumped in the world of infinite CW complexes, even if you were only really interested in finite CW complexes. So, as other examples, if you want to know about K-theory, so vector bundles on a finite CW complex, you need to build BU. If you're interested in cobordism, you need to build MU. And these are all infinite dimensional CW complexes. So, we're going to come across some examples of these infinite dimensional modules as we go along. So I'm going to write mod of kg for the category of all kg modules and homomorphisms, infinite as well as finite dimensional. And we're often interested in a quotient category of this called the stable module category, which has the same objects, but where you think of two morphisms as being the same if their difference factors through some projective module. Okay? And in other words, what we're really trying to do is make the projective modules vanish in this category and just think modulo the projective modules. And the only complicated thing about this is that what you get when you do that construction is not an abelian category, because you can no longer tell whether a map's injective or surjective or anything else, because you can take an injective map and rearrange it to make a map that's no longer injective. Instead, it's what's called a triangulated category. And actually, the translation in this triangulated category is the inverse of this omega function. So it's the co-kernel of an injective hull. And the triangles just correspond to the short exact sequences back in the module category. And if I write little m's for my module categories, I'm going to mean just the finitely generated modules. So I'm going to write proj of h star of g comma k to be the set of all closed homogeneous irreducible subvarieties of v sub g. So that's just the set of homogeneous prime ideals in the cohomology ring. And if you have a subset of this, not the irrelevant one. Actually, I should have excluded the irrelevant one. So everything except the maximal ideal of all positive degree elements. So if you have a subset of this proj that's closed under specialization, which just means that if you have an element in that subset and there's something contained in it, then that's also in the subset. Then you can look at the full subcategory of the stable module category, consisting of modules whose variety is a finite union of elements of this V. So this is just a category with the following properties. If you have two of the terms in a short exact sequence are in this M, then the third is also going to be in this M. And any summand of something in this M is also going to be in this M. So actually that's what we call a thick subcategory. And then the third property is that if you tensor with anything, you stay inside M. So we call that ideal closed. Now, to any such subcategory of the stable module category, there's a construction of Jeremy Rickard that gives a particular triangle of modules. And these modules, E sub v and F sub v, are what's called idempotent modules. They have the property that if you tensor, say, E with E, you get back E plus a projective. There are usually no finite dimensional modules with that property apart from the trivial modules. So these are necessarily infinite dimensional modules. And these modules are characterized by the following properties. The E module is essentially in M, except that M was only consisted of finitely generated modules. So you have to take co-limits of these, or ascending unions of modules in M. So E is essentially in M, and F is about as away from M as you can get. So for any module in M, there are no homomorphisms to F. So this is a bit like if you know about sheaves on some sort of variety. If you have some sort of closed subset, then E would be the sheaf supported on that closed subset, and F would be away from it. So somehow E corresponds to being inside M, and F corresponds to being totally away from M. Yeah, okay. So as an example, let's suppose you just take the set of subvarieties of a hypersurface. Then the way you can build these E and F is very explicit. We're going to represent zeta by a cocycle, the way we did before. And we're going to dimension shift so that zeta is really giving you a map from k to omega minus n of k. You can also dimension shift it to a map from omega minus nk to omega minus 2nk, and so on. And you're just going to take all these maps and take the co-limit of these modules. That co-limit is the F module. Somehow you've localized by inverting zeta here, is really what you've done. And the cohomology of this module F zeta is just the what you get from the cohomology ring if you invert zeta. And then you can just get back the E module by taking this map from k to F zeta and filling in the third vertex of that triangle, which is the same as making it surjective by adding in a projective module here and then taking the kernel. So actually, if you want to see a big nasty diagram, there's a big nasty diagram whose limit gives you the triangle. For more general subvarieties, you can build the E's and F's using this case quite easily. So if V is an intersection of hypersurfaces, you can just tensor together the E modules for those hypersurfaces, and that will give you the E module for your variety. So that tells you what that E module looks like. And then you can get back the F module for your variety by completing the triangle again. So actually, we first built the F module for zeta. We then moved to the left to build the E module for zeta. We tensored those together to give the E module for V. And then we've moved back to the right again to get the F module for V. So it's a little involved. You can't just tensor the F's to get f. It doesn't work like that. So, a very important particular module that you can build this way is called this kappa module, kappa sub v, which consists of you take your E sub v and you tensor with the F module for the collection of subvarieties which doesn't contain v. Okay? So if you tensor those together, somehow what you're doing is you're taking v and wiping out all its proper subvarieties. So all you're left with is the generic point of v. So this kappa module somehow captures the generic point of a subvariety.
Could you not say an open subset of the scheme instead? I mean, I'm so much more used to the language of closed and open subvarieties rather than specialization and generic points by now. But is this just before the examples you were taking were the set of varieties contained in a given closed set.
Yes.
That's what I usually think of
Yes.
as the subvariety.
Right. Right.
And here,
But here we're clearing.
The open set, which is the complement.
Well, you're taking a variety and you're removing all its proper subvarieties. If you just do that at the level of points, you've got nothing left.
This is like a fraction.
Yes, it's a bit like a fraction field. Yeah.
I mean, if I localize at a prime ideal, then I've removed all the primes containing that prime ideal. Right? So,
Yes.
So this is like localizing the ring with the scheme associated with the local ring.
Well, but first of all, you cut down to that subvariety. So you've modded out the prime ideal and then you've localized. So you've got a field.
Oh, I see.
Yes, it really is like a field. Yeah. And actually, one of the things we would really like to understand is what the cohomology of these modules look like. It should just be the injective hull of that field. However, that involves a conjecture that we can't prove yet. I can only prove that in the case where the cohomology ring is Cohen-Macaulay. Where was I? Oh, yes. What time did we start, by the way? 2. Okay, good.
158.
Gotcha. So now, I'm going to tell you what the variety of an infinite dimensional module is. Instead of being a single subvariety, it's a collection of subvarieties. You just want to know which generic modules it has a non-projective tensor product with. So this is a bit like, let's say you have an infinite dimensional module over a Noetherian ring, or an infinitely generated module over a Noetherian ring. You want to know what primes have the property that x star of the ring modular of that prime with your module is non-zero. So that's some collection of primes. It's not closed under specialization usually. It's not quite the support. The support is exactly the closure of that under specialization. So this is the definition of a collection of subvarieties associated to a module. So this is some subset of proj. So for example, if you started off with a finitely generated module, it turns out that the collection is just the set of subvarieties of the usual support variety that we defined before. However, for infinitely generated modules, it's not closed under specialization. In fact, every subset of proj occurs this way. The reason why every subset of Proj occurs this way is because the variety in this sense of this kappa module is just V itself. So you can take an infinite sum of kappa modules and get any subset you like. But again, it satisfies these nice properties with respect to being able to tell whether a module is projective and behaving well with respect to direct sums and tensor products. These are not easy theorems, by the way. None of these theorems are easy. But the other thing is that you can actually calculate these varieties by restricting down to elementary abelian subgroups and without using any cohomology.
What about indirect sums and products?
For infinite direct sums, it's just fine. For infinite tensor products, I'm not sure what that means. I don't know how to take an infinite tensor product of modules.
A limit over the finite subsets.
What are the maps?
Includes.
So you've got some map from the trivial module to your module?
Those are modules, those are not items.
No.
Okay.
No, it doesn't work. So that was a large chunk of machinery I just gave you in rather a short time, for which I apologize. But now let me use it to start to establish some duality theorems on cohomology rings.
The immediate starting point for van der Waarden, who submitted on 14th of August 1925 at age 22 and hardly 9 months after his arrival at Göttingen, an article entitled Zur Nullstellentheorie der Polynomideale, which was published in Mathematische Annalen in 1926. I will show you the opening sentences and some comments on this article in a little while. Let me just end the introduction by taking up the thread I started at the beginning with this definition, the general definition of algebraic geometry, extrapolating just from this bit of the story. A very natural story seems to suggest itself to the effect that what happened to algebraic geometry in the 30s and 40s was a function of new powerful algebra, which was being brought to bear on geometry, transforming this field so as to bring it closer to the algebraic taste of the day. This story clearly, I believe, holds some truth, and it certainly explains van der Waarden's first paper on algebraic geometry cited above, and which I will come back to in a minute. But the goal of my presentation today is to show that this story does not at all give adequate insight into the complicated development of algebraic geometry during the 2 decades, 1926 through 1946. I say 46 because of the publication of the Foundations of André. It is also not the way in which most of the actors or their immediate successors have described the rewriting of algebraic geometry in the 30s and 40s. Consider, for instance, the following quotation by David Mumford from the preface to Parik's biography of Oscar Zariski. The Italian school of algebraic geometry was created in the late 19th century by a half-dozen geniuses who were hugely gifted and who thought deeply and nearly always correctly about their field, but they found the geometric ideas much more seductive than the formal details of the proof. So in the 20s and 30s, they began to go astray. It was Zariski and, at about the same time, they who set out to tame their intuition, to find the principles and techniques that could truly express the geometry while embodying the rigor without which mathematics eventually must degenerate into fantasy. The strong message of this quote is that of a historical continuity and linear progress in the development of mathematics. The injection of new algebraic techniques into algebraic geometry is portrayed by Mumford as a necessary operation in order to save the traditional results collected by the Italian school, in order to truly understand them conceptually. Now, while it is true that a number of claims of the Italian algebraic geometry were very much under debate in the period we are looking at, Mumford's account reflects neither the contingency of the way in which algebraic geometry was finally rewritten, nor the considerable complexity of the historical process in which Zariski's and Wei's breakthroughs was embedded. This complexity is the subject of my lecture. Following the sinuous path van der Waarden's papers on algebraic geometry during the period in question seems particularly suited as a safeguard against undue simplification. So let me now look at van der Waarden. So first of all, how does he get into this? This is so I apologize for the fact that a number of slides are in German and I have not supplied translations, because this talk was first, and the slides were first prepared for the celebration of van der Waarden's 100th birthday in Groningen a few weeks ago. And in Holland, it doesn't pose any problem sort of projecting a German slide and then paraphrasing it in English. I'm sorry, I should have reworked them, but I didn't have the time to do so. I will do my best. This is a letter from Brouwer announcing to Helmut Kneser, at the time Courant's assistant in Göttingen, in 1924, that in a few days, he says, one of my students will come to Göttingen for the winter term. His name is van der Waarden. He is very bright and has already published a few things. And then he asks Kneser to take care of sort of formalities that he may have to do with and so on. And in fact, van der Waarden and Helmut Kneser became friends very soon afterwards. Then here is sort of what I alluded to already in the introduction, the very first paper of van der Waarden's on algebraic geometry, and his own account written in English of how it came about. When I studied Emmy Noether's paper, the 23, this is not visible, but it's the 23 paper on elimination theory and general ideal theory, I saw that the point xi with coordinate xi1 through xim was just the generic point I was looking for. So this is cut out of a more general context. I also saw that Emmy Noether's Nullstellenkörper was isomorphic to the quotient field of the residue class ring O modulo P, where O is the polynomial ring K of x1 through xm. Hence, it was not necessary to go through Hensel's elimination procedure. One could start with any prime ideal P, construct the residue class ring in its quotient field, and thus find generic point of variety of P. I wrote a paper based upon this simple idea, showed it to Emmy Noether. She had once accepted it for the Mathematische Annalen without telling me that she had presented the same idea in a course of lectures just before I came to Göttingen. I heard that later from Grell, who attended her course. And this is how he gets to publish, age 22, this paper in the Mathematische Annalen, where he says in the introduction, I just do this first sentence, the exact foundation of the theory of algebraic manifolds in n-dimensional spaces can only be realized through the means of ideal theory, because already the definition of an algebraic manifold leads immediately to polynomial ideals. And then he is proud of having eliminated elimination theory, so to say, in this particular context. So now let us have a quick look at the literature that we are looking at. So the papers of van der Waarden's on algebraic geometry have been essentially collected, edited by Hirzebruch in this volume, van der Waarden zur algebraischen Geometrie, selected papers. This is not as frustrating as the edition of Hasse's collected papers, but still it is a little annoying because a few important papers are not in there. So this is the first page of the table of contents where I add the years, and this is the second page, and I indicate a certain number of things that should have maybe been in there. So what I just mentioned is this very first paper, where he then makes this first and lasting, very much lasting contribution to algebraic geometry by defining the notion of generic point in a general satisfactory way, which is later on then used by all the people who follow him, in particular Zariski, as we will probably also hear in the next lecture. After that, there are a few papers here in this list that, if you look here, for example, about multiplicity generalization of Bézout's theorem, which concern the problem, which was actually the 15th problem of Hilbert's problems from 1900, of giving a strict and rigorous foundation of Schubert's calculus of enumerative geometry. So he tackles this, and he tackles this in these first papers still by purely algebraic methods, exactly the kind of algebra that he has also brought to bear on the question of generic point. in fact, his interest in the foundation of Schubert calculus predates his Göttingen days. It appears that he was influenced before he came to Göttingen, when he was still in Amsterdam, by a course given by Hendrik de Vries. But anyway, which was a course on Schubert calculus, and that's how he saw the problem. Now, what happens is that while pursuing this problem and writing a few papers on it, he runs into difficulties. And the first turn, I was talking before in the introduction about the sinuous path taken by van der Waarden in the algebraic geometry. The first turn occurs 1928 through 1932, and it is the paper number 5 here from 1920, published in 29, about the topological foundation of Schubert calculus. So what he says in this paper, so this is the first paper where he sort of contradicts what he said in the first paper. In the first paper, remember, he had said the only exact way to do things is using ideal theory and using that for algebraic geometry. Now he gets another inspiration from Lefschetz's method, because I'm not going to go into the technical details, otherwise I wouldn't have time to say what else I want to say, but he just ran in the previous papers into difficulties with this purely algebraic approach, and so looking for help, he turns to a completely different methodological paradigm and comes with a topological notion of multiplicity emulating Lefschetz. This is exactly what he says here. He says, as far as it goes, the algebraic method has a greater generality, of course, than these topological methods, because you can work over any ground field. But if you look at the most general case, sort of having two subvarieties of an ambient variety of complementary dimensions in this ambient variety and try to define their number of intersection, you just hit on problems that you cannot solve in the framework of ideal theory, and therefore he turns to topology. So there is this brief and significant, I think, topological interlude. I also, as you may have noticed, indicate that what happens in his life. So on 6th of May 28, he is appointed ordinary professor at Groningen in the north of Holland, where he was also born, if I remember correctly. But then, subsequently, in 1931, he accepts a job in Leipzig, successor to Otto Hölder, in Leipzig, in Germany. By that time, you should remember, he was already married to Relich's sister Camilla, who is German and who apparently did not like life in Groningen. So there are also personal reasons. But it appears, and okay, so what am I trying to say about this Leipzig job? First of all, this is a little clipping from the letter of the faculty justifying why they want van der Waarden as number one on their list, why they want to hire him. And this is the bit where they talk explicitly about his topological turn in the foundation of Schubert calculus, and say how wonderful this is, how good mathematics this is. But in fact, what sort of, as far as mathematics or science is concerned, interested van der Waarden most in Leipzig at the moment of accepting his job was the possible contact with the physicists there, because at that time Heisenberg and Hund were in Leipzig, and van der Waarden was very much interested in this. He gave his inaugural lecture on the group theory as a ordnendes Prinzip. How do you say this? As a principle that, Organizing principle, thank you, and thinking in particular of quantum mechanics. This is when his book on quantum mechanics appears. So it's not so much for algebraic geometry that he wants to go there. So this was the first term. Now comes the second term. The second term occurs in 1932, and this is the way van der Waarden tells the story himself. At the Zurich International Congress in 32, I met Severi, Francesco Severi, and I asked him whether he could give me a good algebraic definition of the multiplicity of a point of intersection of two varieties of complementary dimension, on which the point in question is simple. The next day, he gave me the answer, and he published it in German, by the way, in the Hamburger Abhandlungen in 1933. He gave several, and so on and so on. So this is the beginning of a new phase and a very important and lasting influence in van der Waarden's work on algebraic geometry. He apparently decides, after having met Severi and after this encounter where Severi proposes this algebraic definition of multiplicity, which I'm again not going to go into, he decides that it is a good idea to try to work together and in contact with Italian geometry, as in particular represented by this towering figure of Severi. And so, for example, there is a letter written by Courant to Tisdale of the Rockefeller Foundation asking for a grant for van der Waarden to go to Rome to, in particular, so he says, Courant says in this letter of March 33, this is a few weeks before Courant will be thrown out of the Math Institute in Göttingen, he says that, in fact, in Germany, the algebraic geometry is practically dead. The tradition is dead, and so we have to refuel it. Now, there were already German scholars, namely Fenchel and Kähler, who have spent some time in Italy on a Rockefeller stipend, and van der Waarden, as a very promising young fellow, should definitely be given the same possibility, and in particular the contact with Severi in Rome will be good for German algebraic geometry or for a collaboration of the two. And van der Waarden himself, in his application, states explicitly that he wants to collaborate with Enriquez and Severi. Severi is the man from which I hope to learn most. Then Tisdale has this note in his diary where he mentions that Princeton wants to get him. These are quotes that I just take from Sigmund Schulz's book. And it is not entirely clear to me why this never came about, whether the Rockefeller Foundation denied the demand or whether the new political situation made it impossible for the Rockefeller Foundation to finance van der Waarden. This is Sigmund Schulze speculates that this was the reason why the foundation didn't give him this grant, but I'm not sure this is the correct interpretation. I think we are lacking some information. So let me remind you of this quote that you have already seen. What we see in van der Waarden's reorientation runs very much against this a posteriori assessment of what happened, you see. Looking backwards, what Mumford says is, well, there were these Wey and Zariski, and they just had to bring some order to the whole thing. But van der Waarden is exactly trying to do something else. He's trying to collaborate with the main and most productive representative of the Italian school of algebraic geometry in order to clearly bring his knowledge of algebraic methods to this school, but in order to have sort of not a revolution or a complete upheaval or a complete rewriting, but sort of a natural development profiting from all the competence that was already present in the Italian school. So now, how does the story continue? We are actually here now, and I want to talk about what I indicated by this black line. The black line separates those papers submitted for publication before and after the advent of Hitler at power in Germany, the advent of the Third Reich. Now, the very first of these papers does not show any significance, but then the next one, this one here, which was submitted on 11th of October 1933, has an introduction which is absolutely surprising. He comments, so first of all, as you probably notice by looking at this, his publications contain in particular that series which is called ZAG, zur algebraischen Geometrie, on algebraic geometry, 1 through, 18 or so. And this is number 6 in this series. And he comments now, for the first time, on the goal of this series of publications. He says, the goal of this series of treatises on algebraic geometry is not only to have to find new theorems, but also to communicate or to bring to the readers of the Mathematische Annalen the far-reaching methods and concepts of the Italian geometric school, but with exact algebraic foundations. Then he the apparent goal of this first paragraph is to apologize if he gives a proof of a theorem which may already have been proved in a strict way elsewhere. So he probably it's a safeguard against criticism from the Italian side. Why does he prove this again and not quote my proof that I already gave? So he says, I cannot look for all the maybe correct proofs that exist. I just do my own way. But there is this thing here, which I have underlined in green, where, first of all, he talks about the Leserkreis der Mathematischen Annalen, that is, the readers of the Mathematische Annalen, and then it sounds as if this number of readers there is almost defined with another group of people, namely der Deutsche von heute, the German of today. And that is Nazi lingo. It's very clear in 1933 that if you speak of der Deutsche von heute and of the difficulties of what der Deutsche von heute can understand and cannot understand, you know what you mean. So please don't get me wrong. I'm not saying that van der Waerden was a Nazi. What I'm saying is that he was living in Germany, he continued to live in Germany, and he is picking up, and maybe even picking up more readily than others, because he was a foreigner and had maybe different ears for the German language, the changes in the language environment that there was. And so this, what comes together here is, on the one hand, his interest in collaborating with the Italian school of algebraic geometry, and on the other hand, the political situation in Europe, in other words, the fascist axis between Germany and Italy. And this is what is brought out quite clearly. I jump a little bit just to bring out this point and then turn to other things. In his book that he finally publishes, The Introduction to Algebraic Geometry of 1939. You see, there is a book by van der Waerden, Introduction to Algebraic Geometry. I think it is not at all read anymore today, has been completely superseded by Weiss Foundation first and then what was to come afterwards. And in fact, when you open it, it's very surprising for us. I mean, it looks like Severi almost. I'm exaggerating. It does not at all have the same ring to it as the modern algebra had when it came out in 1930. So in the preface of this, he says, this is picking up a thread that I was indicating at the very beginning. He said, I started out from ideal theory, but this ideal theory that I have used in my earlier investigation has now proved to be not necessary in the foundation of algebraic geometry. Instead, it is replaced by the more far-reaching methods of the Italian school. So this marriage between algebra and Italian school is really supposed to be completely realized in this book. And then this is the preface. Then in the introduction, he says that algebraic geometry has arisen from the organic melting of the theory of algebraic curves and surfaces, highly developed in Germany, with the geometry with higher dimensional geometry of the Italian school, and so on and so on. And the reaction to this book is exactly along the lines that I try to indicate to you. This is the Centralblatt review written by Fabio Conforto. Questo volume, etc. Non si trova invece